Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH and equilibrium concentration of all species present in a solution with known concentrations of a base and the conjugate acid of that base, which is present as a salt and as a common ion. In this specific problem, you're asked to calculate the pH and the equilibrium concentrations of all species present in a solution of 0.25 molar ethylamine and 0.20 molar ethyl ammonium chloride. The first thing you want to do for this type of problem is to identify the species present initially and their acid-base properties. The first species we can identify as being present initially is ethylamine. And ethylamine is a base. It will accept protons. Another species present is chloride. So chloride comes from the ethyl ammonium chloride when it dissociates in solution. And when that happens, you get the ethyl ammonium ion plus the chloride ion. So chloride is considered inert in acid-base chemistry because it's one of those anions coming from strong monoprotic acids that do not react appreciably with water in a way that changes the acid-base properties of the solution. Another species present is the ethyl ammonium cation, which is what appears in solution when ethyl ammonium chloride dissociates. So the ethyl ammonium cation is C2H5NH3+. And this is the conjugate acid of the ethylamine base. So we know that this acts as an acid. And finally, the fourth species present initially is water, and water can act as an acid or a base. The next thing you want to do is identify the possible proton transfer reactions so that the principal reaction can be identified. So the principal reaction is the reaction that's going to head the ice table. So as you can see, there are two acids and two bases that can be the reactants in these proton transfer reactions. So that means that there are four possible proton transfer reactions when you combine these two acids and two bases in various ways. The first reaction we're interested in is where our base, ethylamine, accepts a proton from water to give the conjugate acid, the ethyl ammonium cation, plus hydroxide, which is what's left over when water donates a proton to ethylamine. The Kb value for this reaction is 6.4 times 10 to the negative 4, and you can find that value in a table of base dissociation constants. Another possible proton transfer reaction between an acid and a base is where acid acts as where one water molecule acts as an acid and another water molecule acts as a base. So when that happens, you get a hydronium ion, which is what's left over when one of the water molecules accepts a proton, and hydroxide, which is what is left over when the other water molecule has given up a proton. The equilibrium constant for this reaction is a special equilibrium constant Kw, or the ion product constant, and it's equal to 1.0 times 10 to the negative 14th. Another possible proton transfer reaction between an acid and a base is where we have the base, ethylamine, accepting a proton from its conjugate acid, which is present initially because It comes from the ethyl ammonium chloride salt. When that happens, you're left with the same thing as a product. You have the ethyl ammonium cation present because that is what is left over when the second reactant transfers a proton to the first reactant. And what's left over of the second reactant when it has transferred that proton is ethylamine. Because the reactants and products in this reaction are the same, it has a K value of 1. Another and final possible proton transfer reaction is where water acts as a base and the conjugate acid of ethylamine, this ethyl ammonium cation, transfers a proton to water. And when that happens, you're left with the hydronium ion plus the ethylamine base. Now the K value for this reaction is very, very small. And we can rule out this last reaction as the principal reaction because ethylamine is a much stronger base than water. And that is the first reaction here. So that has a much larger Kb value than this last reaction will have. So we can rule that one out as a possibility for the principal reaction. The third reaction shown here does have the largest K value, but it doesn't change any of the concentrations, and we need to see a concentration change in order to solve this problem using an ice table. So the third reaction also cannot be the principal reaction that heads our ice table. So we're left with the first and the second reaction, and of those two, the first reaction has the largest K value, so that is going to be the principal reaction that heads our ice table. So here we go. Let's make the ice table. We have ethylamine accepting a proton from water to give the ethyl ammonium cation plus the hydroxide anion, which is what is left over when water transfers a proton to ethylamine, which is our weak base. So now we can think about the initial concentrations, the change in those concentrations to reach equilibrium, and the equilibrium concentrations. So we're given in the problem that we have 0.25 molar ethylamine. So that is the initial concentration of ethylamine. We're also given that we have a 0.2 molar initial concentration of ethyl ammonium chloride. So if you look back at the reaction showing the dissociation of ethyl ammonium chloride in solution, you can see that there is a 1-to-1 molar ratio between ethyl ammonium chloride and the ethyl ammonium cation. Therefore, if we have 0.2 molar ethyl ammonium chloride, we also have 0.2 molar ethyl ammonium cation. So the initial concentration of that ethyl ammonium cation is 0.20 molar. And the initial concentration of the hydroxide ion is approximately equal to 0. For the change in concentration, we're going to say that the concentration of ethylamine changes by -x, and if that's the case, because we have a 1-to-1 molar ratio between that reactant and our two products, then the change in concentration for our two products is going to be plus x, because for every mole of ethylamine that's lost, we gain 1 mole of the ethyl ammonium cation and 1 mole of the hydroxide anion. Now we can write the equilibrium concentrations of all the species present in terms of x. So we get 0.25 minus x for ethylamine. We get 0.20 plus x for the ethyl ammonium cation, and we get x for hydroxide. So now we're going to want to use the equilibrium expression and our known Kb value for the principal reaction to solve for X. So we know that Kb is equal to the products over reactants for the principal reaction. So we have the ethyl ammonium cation concentration multiplied by the hydroxide ion concentration divided by the ethylamine concentration. We know that our Kb value is equal to 6.4 times 10 to the negative 4 because we've looked that up in a table of base dissociation constants. According to the ICE table, the concentration of the ethyl ammonium cation in terms of X is 0.20 plus X. The hydroxide ion concentration is X. And finally, the ethylamine concentration in terms of X at equilibrium is 0.25 minus X. So it'd be nice, as always, if we can get rid of these two X's because that would make solving this equation much easier. So in order to do that, we'll make an assumption. Well, two assumptions really. We're going to assume that 0.20 plus X is approximately equal to 0.20 and that 0.25 minus X is approximately equal to 0.25. So what this is really saying for both of these cases is that this X value is so small that adding it to 0.2 or subtracting it from 0.25 will not change those values. So to test the assumption, we need to go back to this equation, integrate this assumption, and solve for X. So when we do that, we get 6.4 times 10 to the negative 4 is equal to 0.20 times X divided by 0.25. Multiplying both sides by 0.25, you're left with 1.6 times 10 to the negative 4 is equal to 0.20 times X, and dividing both sides by 0.20, you're left with 8.0 times 10 to the negative 4. So here is our X value. We need to go back and test those assumptions by substituting in the X value. So we have 0.20 plus X. Substituting in the X value, we have 0.20 plus 8.0 times 10 to the negative 4. If you do the math there, you get 0.1992. Rounding that to two significant figures will give you 0.20. So adding X to 0.20 does not change its value, and you'll see the same thing when you subtract X from 0.25. So we have 0.25 minus 8.0 times 10 to the negative 4 is equal to 0.2492. Rounded to two significant figures, you have 0.25. So it's okay to make the assumption, and because of that, we've already solved for X. So we can go back and find the concentrations in our ICE table. So we know that the equilibrium concentration of the hydroxide ion is equal to X according to our ICE table. So we know that the concentration of hydroxide is 8.0 times 10 to the negative 4 molar. So there's one of those concentrations we were looking for. Another concentration we want to know is the concentration of ethylamine, which we've defined in our ICE table as 0.25 minus X, and we already know from the assumption that we tested up here that subtracting 0.25 from X indeed gives us 0.25. So the concentration of ethylamine is 0.25 molar. So there's another of the concentrations that we want to solve for. We also want to solve for the concentration of the ethyl ammonium cation, which is C2H5NH3, and in our ice table we've defined this concentration in terms of X as 0.20 plus X, and we've already seen by testing the assumption here that adding X to 0.20 does not change the value, so we know that the ethyl ammonium cation concentration is 0.20 molar. Another of the concentrations that we need to find is the hydronium ion concentration, because that's another one of the species present. We know the relationship Kw is equal to the hydroxide ion concentration times the hydronium ion concentration. So we can rearrange things and say that the hydronium ion concentration is equal to Kw divided by the hydroxide ion concentration, and we can substitute in values that we know here, which are the Kw value, which is 1.0 times 10 to the negative 14th, and we just solved for the hydroxide ion concentration up here, and we can substitute in that value 8.0 times 10 to the negative 4, and when you do the math there, you get 1.3 times 10 to the negative 11 molar for the hydronium ion concentration. The last thing you need to do here is find the pH. So the pH is equal to the negative log of the hydronium ion concentration. So if you substitute in the value for the hydronium ion that you found, take the negative log of that, you get a pH of 10.9. So we've solved for the concentration of all species present, and we've solved for the pH. So we're done.